Alright, let's start off with problem number 2 in chapter 10. Our task here is to find the internal reactions at point M here in our support member here. So that means we'll be finding the axial force, the shear force, and the moment. The internal reactions are the forces that keep this whole structure here at static equilibrium, even though there's a big load of whatever, maybe rubble here or something. So to visualize what those forces are, let me ask you to imagine that we actually take a big sword and slice through our member here at point M. And think what would happen once we did that. Well, the top piece would fly to the left because of this force. It would fly downwards because of that force. And we can see that it would also start rotating counterclockwise. So these internal reactions that we have to find are the forces that are applied from right here, right under point M, to our top piece of wood or whatever it is. So when this thing is all in one piece, before we cut it with our sword, it's in static equilibrium. So that means that the sum of all axial up and down forces is going to be 0. And we have a big down force here that must be countered by an upward force acting here. So the math here isn't really too hard. 7.5 kilonewtons minus whatever the upward force here equals 0. So we can see that this axial force must be 7.5. And we know this is an axial force because it's along the length of the rod. That's as opposed to the force here that's perpendicular to our rod or beam or whatever. Because this 3 kilonewtons is perpendicular, it is a shear force. But it's the same story with the shear force. Whatever, the sum of all forces in the left and right direction must be 0. So this 3 kilonewton force to the left must be countered by a 3 kilonewton force to the right here. And I almost forgot sign conventions. Let's go back to the axial force, this 7.5 kilonewtons. We know that this is a compressive force because it's trying to shorten this part of the rod instead of lengthen it. So since it's compressive, it is actually negative, so we put in a little negative sign there. So negative 7.5 for our axial force. Okay, now for the tricky one, the moment. So this one, the moment is all about rotation. If you've talked about torque in physics class, it's pretty much exactly like that. It's the force times the moment arm. So before we go any further, let's really cut this thing at M. There we go. That simplifies things a little bit. When you're doing these kind of problems and you're trying to find the internal reactions at some point in a beam or column or a rod or whatever, you can just look to one side of that point. Here it's point M. So we just look at everything above M, and it doesn't matter what was down here. So when we're asked to find the internal moment, it's asking us, if this is a steel member, it's asking us to find what is the moment being applied right here, right under where we cut, that keeps this whole member from rotating like that. So we know that the moment has to oppose both the moment created by this 3 kilonewton force and the moment created by this 7.5 kilonewton force. So again, we have a static equilibrium. We have a situation where the sum of all moments is 0. So if we add the moment from the 3 kilonewton force, that moment is the force times the moment arm, which is the distance from where the force is applied right here to the location that it would rotate around. So here at point M is where the axis of rotation would be. So the moment from this 3 kilonewton force is 3 times 0.4. And then we have to add to that the moment from the 7.5 kilonewton force. And that moment is 7.5 kilonewtons times the moment arm of this one. So finding the moment arm here is a little more tricky. What we have to do is find where this force line has a right angle to a line from that axis of rotation, and it's right here. So this distance would be the moment arm, and that's the same as this 0.4 meter distance. So again, our moment arm is 0.4 meters. Alright, and so what we've got so far are these two moments that are trying to rotate our member counterclockwise, and that means our internal moment being applied here has a magnitude equal to these two, but in the other direction. So we know that it's going to be trying to rotate the member that way, clockwise. And if we go ahead and solve this equation and do some math, let's see. 3 times 0.4 is 1.2. 7.5 plus times 0.4 is exactly 3. And we've found the value for the internal member at point M.